If we look at the reactivity series of elements, this means the susceptibility of cations to be moved through electrical current. And so if we're going to range from the most susceptible to the least, so we look at it, potassium's the starting point, sodium, calcium, magnesium. The four major cations of soils. There's no accidents here. Aluminium, that can be a major problem. Carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold, platinum. And we know that silver can be used, like that's how you get colloidal silver, running electrical charge between two electrodes, and the colloidal silver goes into solution. So, what we're going to look at, when you're looking at base saturation of soil, you've only got 2% potassium, but you actually end up with 3% in the composition of the plant, or roundabout. I kind of like to get it lower than that, but this gives a relationship to the amount of other nutrient in the soil. How did that get to there more than, say, the calcium that was 70%? And this is all relating back to the most susceptible to the least and to electrical current. Now, if we go back to the start in Faraday's laws, and where it was discussed about the amount of movement that you'll have, the law stating the amount of any substance deposited or liberated during electrolysis is proportional to the quantity of electrical charge passed and to the equivalent weight of the substance. So Faraday's law actually matches up perfectly with this here. So you're looking at the amount of the electrical charge going through the soil and the weight of the substance in here against the reactivity series. So if you change the amount of electricity, there's going to be more nutrient moved. So the idea is to actually enhance the electricity, but have all of the cations in order to actually have a really beneficial effect. So as I've said, in nature we can see, if we go to the beach, we can actually see the shells corrode into the sea. And there's other things in the sea that do show interesting parts too. It's like in the sea, the aluminium actually drops down lower than the zinc, and the zinc goes up higher than the aluminium. And this shows when you're using a sacrificial block on boats, crayfish pots, all sorts of things, where aluminium boats, you'll put a zinc block on the aluminium and it will corrode instead of the aluminium. As soon as the zinc block's gone, the aluminium starts, or the iron, or whatever you're trying to protect, brass props. So things change depending on the composition of the soils, just the same as it does in the sea. Now, if you put a zinc block out in the paddock and you've got galvanized gates and all that sort of stuff, and you put a piece of aluminium down, the aluminium will corrode really fast compared to the zinc. Interestingly though, as you start to change the soil biology patterns, mineralogy, and get that pH up, then we start to see this aluminium go into those hydroxyl forms we talked about earlier, and they don't become an issue. Now, it is a major issue if you're looking at low pH soils. You do not, with high aluminium, you do not want to be poking a lot of electrical charge in there, because I can tell you, you will be bringing up the aluminium like it's going out of fashion. And you end up creating flatweeds with little silvery, shiny antennae type looking on them. And the animals do not do any good at all, and the soil really shuts down. So this is part of the interesting scenario, that when you're bringing physics, chemistry and biology together, it's essential to actually have them working all in unison instead of doing them apart. Now, I've come across this issue myself. I'm rather glad that I found it out myself. We would use a lot of the product we call Probitas and create a lot of electricity on high aluminium soils that didn't have a lot of calcium and magnesium, and we couldn't get the soil depth, and it didn't have any silica available to sop up the aluminium, and we shut the place down in a big way, and it was very detrimental to the livestock as well. So that's why we're taking such a considered approach when we set everything up to move forward. Once you understand what's going on, you need to put everything in proportion and understand that they're trying to lock away the aluminium, they're trying to make the trace elements more available. And that happens too with this, when the copper, when this is put in the ocean, that starts to come up. So these are things that we actually need in agriculture. We don't need the tin and the lead. We want these the zinc, iron, copper, all to come up and the aluminium to disappear down below. So When we understand that in the reactivity series, that's why we start to try and bring C elements back onto the shore to get the reaction that we're requiring.